Welcome. Today, we're diving into Computational Learning Theory, or CoLT. It's a branch of theoretical computer science and artificial intelligence that provides the essential mathematical foundation for machine learning. Instead of focusing only on specific algorithms like neural networks or decision trees, CoLT explores the fundamental principles and limits of how machines can learn effectively from data. At its heart, CoLT seeks to answer critical questions. How much data is truly necessary for an algorithm to learn a concept reasonably well? What are the inherent computational limits, in terms of time and memory, required for learning certain tasks? How can we mathematically measure the intrinsic difficulty of a learning problem, or the representational power, often called capacity, of a learning model? And crucially, what kind of guarantees can we provide about the accuracy and reliability of the models learned from data? Several key ideas form the foundation of CoLT. Perhaps the most famous is probably approximately correct, or PAC learning, introduced by Leslie Valiant. The goal here isn't necessarily perfection, but finding a hypothesis that is probably meaning with high confidence, approximately correct, meaning with low error. PAC learning helps us quantify the difficulty of learning tasks by analyzing the sample complexity, the minimum number of training examples needed to achieve a desired level of confidence and accuracy. A related concept is the Vapnik-Chervonenkis dimension, or VC dimension. While PAC learning looks at the problem, VC dimension quantifies the capacity or complexity of a specific model or hypothesis space. It measures the maximum number of data points that a model can perfectly classify for every possible labeling, a concept called shattering. A higher VC dimension indicates a more powerful model, capable of fitting more intricate patterns, but it also demands more data to learn well and carries a higher risk of overfitting learning noise instead of the true underlying signal. Conversely, a model with a low VC dimension is simpler, but might underfit, failing to capture the complexity in the data. VC theory provides vital mathematical bounds that connect the model's VC dimension, the number of training samples used, and the expected error on unseen data. Beyond PAC and VC, CoLT encompasses computational complexity analysis, whether learning can happen in feasible time, understanding the bias-variance trade-off, which relates to model complexity, analyzing generalization, how well a model performs on new data, and the theory behind regularization methods used to prevent overfitting. So why is all this theory important? CoLT provides a rigorous framework to analyze algorithm performance beyond just empirical tests. It allows us to provide formal guarantees about when learning is likely to succeed and how much data is required. It helps us understand the fundamental limitations of what can be learned efficiently. Crucially, these theoretical insights guide the development of new, more effective algorithms. For instance, boosting algorithms have roots in PAC theory, and support vector machines are strongly linked to VC theory. The principles of CoLT are deeply embedded in modern machine learning practices, even if practitioners don't always calculate VC dimensions explicitly. Theory informs model selection, preferring simpler models with less data. It guides algorithm optimization for efficiency, and provides theoretical justification for techniques that improve generalization. Even in the complex world of deep learning, researchers are actively working to extend or adapt CoLT concepts to better understand why these incredibly complex models often generalize surprisingly well. Looking ahead, CoLT is evolving to address new challenges. A major focus is developing better theories for deep learning. Other active areas include extending guarantees to online learning and reinforcement learning, incorporating notions of fairness and robustness into the theory, and developing frameworks for explainable AI. In conclusion, computational learning theory provides the essential mathematical language and conceptual tools to rigorously analyze and understand machine learning. It moves beyond just observing what works to establishing the fundamental principles governing how algorithms learn, generalize, and operate efficiently. While practical applications often combine theory with heuristics and experiments, the foundations laid by CoLT are indispensable for guiding algorithm design, ensuring reliability, and pushing the boundaries towards more powerful, efficient, and trustworthy artificial intelligence systems.